Hi, I'm Tim Baumgartner from UKP Lab at TU Darmstadt, and this is joint work with Irina Gurevich on whether large language models can tell when a paper and its code disagree. We built the SciCoQA dataset to find that out. In this presentation, I'll show you three things. First, why the paper code alignment task matters for reproducibility and for trust in AI scientists. Second, how today's best large language models perform when you ask them to check it. The headline is going to be high precision, low recall, and you'll see exactly what that means. Third, what we should do about it. Let me start with one real example from a published paper and its open source implementation. In the paper, it says, two networks produce a variance sigma and a shift mu. Their output is unconstrained. Now look at the code. The film block applies a sigmoid to both mu and sigma before they're used. Sigmoid clamps everything into the interval 0 to 1. So the paper promises an unconstrained affine transformation, but the code scales by a positive number between 0 and 1. The network the paper describes and the network the code implements are not the same. Let me generalize from this one example. We define a paper code discrepancy as a semantic conflict between what the paper describes and what the code actually implements, meaningful enough to alter the scientific logic, the experimental protocol, or the math. And it helps to say what it is not. It is not a bug, the code runs cleanly. It is not a configuration mismatch. There's no command line flag that flips it. And it is not a nit, like adding an epsilon to a denominator for numerical stability. It is a genuine conflict between the science described in the paper and the science in the codebase. Why does this matter? Because a paper and its code can disagree silently, and right now nobody reliably catches it. Three reasons we should. Reproducibility. Releasing code is treated as proof of reproducibility, yet research still ends up irreproducible. An automated paper code consistency check adds a missing layer. AI scientists. Agentic systems can now write the paper and the code end to end. If a system writes both, it can easily write a paper that doesn't match its code, and that output needs verification at scale. Peer review. Reviewers face more submissions with less time each. An automated check can confirm paper and code agree before a human even opens the repo. The question now, can today's language models catch these discrepancies? To answer it, we first need ground truth data. We build it on two tracks. We collect real-world discrepancies from GitHub issues and reproducibility papers from venues like the ML Reproducibility Challenge. We manually filter out non-discrepancies, then have Gemini and GPT-5 verify and rephrase each one to standardize the ground truth. Real data is authentic but scarce, so we synthetically scale it. We take scientific code bases spanning various computational science domains, including AI, physics, and quantitative biology. Then GPT-5 plants plausible, conceptually meaningful code diffs in the repos. We call this dataset SciCoQA. This yields a total of 635 paper code discrepancies from 276 papers across 6 computational science domains. Now we have the data. Here's the task and how we evaluate it. We give a model the full paper and the full code base in context and prompt it to list any paper code discrepancies. We run 22 models, closed and open, reasoning, instruction tuned, and code specialized. The subtle part is evaluation, and we do it two ways. First, recall. Did the model find the discrepancies we know are there? A judge model matches each prediction against our ground truth dataset. But the judge can't tell whether a flagged discrepancy that isn't in our data is a false alarm or simply one we never annotated, so automatically we can only measure recall. To measure precision, that is if the flagged discrepancies are actually real, we need human verification. On 20 papers, we manually audit every prediction and pool all verified ones. From this set, we get precision. Here is our main result. First, recall on the automatic benchmark across all 635 discrepancies. The best of our 22 models finds only 46.7% of the real-world discrepancies, less than half. Second, precision with the human verification. Here, when a model flags a discrepancy, it's right up to 95% of the time. But the recall on those same papers stays at 41 to 56%. Low again. And notice the trade-off. No single model wins both. The most precise, Gemini 2.5 Pro, has the lowest recall. So we find that models have high precision but low recall on the paper code alignment task. That is the headline finding of our paper. Where does recall actually fail? Let me slice GPT-5's recall three ways. 1. The type of discrepancy. We have 3. Differences where paper and code conflict. Code omissions, where the code skips something the paper specifies, and paper omissions, where the code does something the paper never mentions. The paper acts as a specification, so the first two can be checked against it. but a paper omission has no textual anchor at all, which makes it the hardest. The model must recognize logic the paper is silent about. 2. A question for you. What do you think happens to recall once the paper and the codebase together exceed 100,000 tokens? Recall drops sharply from 78% on the shortest inputs to 52% past 100,000 tokens, and 73 of our 276 papers cross that line in our data. So SciCoQA is also a serious long context benchmark. And 3. Papers published after the model's pre-training cutoff. Most models perform worst on the most recent 2025 data, consistent with prior findings on contamination. That's exactly why we generate synthetic data. It tracks real recall at a high correlation, so we can refresh the benchmark with uncontaminated samples as new models land. What do we do with all this? 2 things, one for today, one for tomorrow. Today, high precision means we can deploy these models to surface candidate discrepancies for a human reviewer. But low recall means we cannot yet certify that the paper actually matches the code if the model flags nothing or all flags have been fixed. Tomorrow, as AI scientists become deployed, every generated paper code pair needs a verifier. The benchmark for that verifier and the path to improving it is what SciCoQA gives the community. Without a benchmark, the AI scientist loop has no oversight. To wrap up, we contribute the task, the first benchmark for cross-modal paper code quality assurance. We contribute the data, 635 discrepancies across 6 computational science domains with a synthetic pipeline that keeps it refreshable. And we contribute the finding. Frontier large language models have high precision but low recall. They can assist a reviewer. They cannot yet replace one. The benchmark is open. Help us build the methods that close the gap.